Hello, everybody. Good morning to Brazil. Good afternoon to Austria. I'm very happy to introduce to you our speaker for this session, Professor Dr. Helmut Habersack. He's Professor of Hydraulic Engineering and Modeling and Head of the Institute of Hydraulic Engineering and River Research at the University of Natural Resources and Life Sciences in Vienna, Austria. He's currently President of the International Commission for the Hydrology of the Rhine Basin, Vice President of the World Association for Sedimentation and Erosion Research, UNESCO Chair on Integrated River Research and Management, and also head of the Christian Doppler Laboratory for Advanced Methods in River Monitoring, Modeling, and Engineering. And obviously he has a vast experience in sediment transport, hydropower, river engineering, morphology, restoration, flood risk management, but also in ecohydraulics and navigation. So it's an honor for us to have you with us, Helmut, and I give you the word to make your presentation on reservoir sedimentation. Thank you very much for being with us.
Thank you very much for the kind introduction. I'm very happy to be here. It's really an honor for me to be with you. Unfortunately, not physically, but with the new methods, it's possible to speak to you as well in this. I hope you can understand me. I try to be not too fast. Today the topic we selected together with the organizers is reservoir sedimentation, assessment, and management. I have the following outline of my talk. I would like to do an introduction to the topic and then to shortly look into the importance of sediment management at various scales, because the whole thing doesn't start only at the reservoir, but it starts in the catchment, as we also know, and it doesn't end in the reservoir, it goes even downstream, as we also know. The third part is then the sediment management in reservoirs, and the assessment is part of it. And then to look into the sediment management from the perspective of a sustainable river management in an integrated way. And then I would like to have some summary and an outlook. And of course, we can have a discussion afterwards. Now, I would just like to start with this slide here. What we have is either too much sediment, as you see it on the left pictures. Maybe you see my mouse here. And you have a deficit on the right side, so not enough sediment. If we have too much sediment, and we all know it, and not enough measures, we end up with reservoir sedimentation, which is the topic of this presentation. And what to do with this, like this one, this picture is here from a weekly reservoir. So in one flood, it can be completely filled up with sediments, also combined with trees. And we have not the reservoir volume anymore for electricity production. So something has to be done here. And on the right side, if we have a sedimentation here downstream, we might get this here, like the riverbed was up there before, and it's now, after 50, 60 years, 1.5 meter lower. And all the bank protection, as you see there, are in the free area. So there's a lot of risk for erosion and damages in flood conditions. Or you see here bridge abutments with erosion and scouring along bridges and bridge piers as well, which can then ultimately lead to collapses of bridges, which we also observe in Europe in various different places. So the main question is, one has too much sediment and the other one has not enough sediment. Why not get into contact and try to improve the overall situation? And in order to do this, we have to start, as I said at the beginning, not only at this spot here or here, we have to look into the system. And this was tried here in a schematic drawing. So we all know that we have different scales here. And with our reservoir, we are mainly in the local scale, to my point of view. Very much determined by the sectional scale, what is the input of sediments from the upstream area, which in itself comes from the catchment side. And then, of course, even the continental or local, regional scale plays a role. Of course, Brazil is so large that it's in itself a very large region, but there, of course, geology, tectonics, and climate change also plays a big important role. So at the end, the sediment comes from the upstream part, determined by the climate change, by land use change in the catchment, of course, determines then the river situation, if you have regulation or not, the continuity interruption, and it ends up in the reservoir. And then, of course, we have as well then smaller scales like this one here within the reservoir or downstream with a point scale. That's the scale where we take samples. So we go out and take a grain size distribution, and then we end up with a point scale. And the interesting thing is that in different scales, you have different processes that determine in a hierarchical way, the larger dominates the small one. So we already discussed the catchment and let's say precipitation distribution, but also the valley development, the valley form, and the erosion potential is here important. Whereas when it comes to the sectional scale, the morphology determines the situation, the slope, the width, depth, the shear stress maybe, and also the sediment supply, for example, or the sediment balance. When it comes to the local scale, we have here additionally bed forms that are important. How is the sediment transported in dunes or anti-dunes? Are there islands and bars? Do we have bank erosion or not? And when it comes to the local scale, of course, we have here the point scale. We have here other processes like sediment transport, initiation of motion. When is a particle moving? What is with grain sorting? You know, we have hiding effects, we have exposure effects, we have different flow velocity, turbulence, and all these influences the initiation of motion. We could go much further into only this one because, for example, in our lab, we did recently only scale models for one single particle. So you can even spend your whole research life to understand why is a particle transported, because then we get turbulence and vortices and things like that. But anyway, in our now in this talk, I think we have to focus on this area here. And once the main point is we have to understand the process. So we cannot really start in this box here before we don't understand what is the key processes, the key sections, the boundary conditions in the larger scale. So normally what we would like to do is to look into a river basin. I know it can be very large in Brazil, but look into that and try to get a sediment balance for the whole basin, focusing of course on the reservoir you want to look at, but then you know when is sediment coming, how much is coming, which grain size is coming. And then, of course, we do the measurements in the smaller scale in a way when it comes to samples. And then important, so this is a downscaling phase, which we would suggest at the first phase. And then we can provide an upscaling following the downscaling, which means then we aggregate the data which we collected here to come up with measures at the local scale, maybe just, and we will see some examples later on. You can have also results for the sectional scale, what to do there. And you can have also measures for the catchment, for example, if you want to go for land use change in order to reduce the sediment supply. So in a way, once we have understood in the first step what is the process, we can use models then to aggregate the information and to derive then measures fitting to the scale. You can look at it also like this in the longitudinal section where you have the mountain somewhere, the water comes there, you might have a reservoir here, you might have a runoff scheme here, and then you have all agricultural areas along the river. This is just some pictures of Austrian reservoirs. This is the largest reservoir we have, and this is one of the largest runoff schemes at the Danube River. So at the end of the day, we have here, of course, sediments coming in, and this is changing if you have glaciers. Obviously, in our country, we have still many glaciers. So when they are melting, then we get more sediments into the reservoir. So we get a huge change nowadays with also thawing of permafrost, getting more sediments on average into the, the reservoir. Then it's filling up here, as you see. And then we have starvation on the one side, of course, material downstream, but we have also additionally land, surface and soil erosion from the agriculture filling up the other reservoirs. So you might have a situation where you have some erosion somewhere, and then you might have sedimentation with fine material, with all the pesticides and nitrogen, phosphorus, and all other substances associated with it. So you might want to know how many tons per hectare per year are eroded, and how much is the uplift of the alpine environment, the mountains, like here 1.6 millimeter per year. You wanted to know, and you should know a little bit more about the erosion of the riverbed, of course, also on the sedimentation. So we need monitoring. It's very important. Without that, we can't really do things. Now, if we want to dredge material, for example, and we want to dump it somewhere, the costs are very high. So in our country, we say it's about 10 to 20 euros. It's approximately the same for US dollars per cubic meter. So if you have millions of cubic meters somewhere in the reservoir and you want to dredge it and dump it, it's very costly. If you can leave it in the system for downstream purposes, it's of course cheaper. Still, you have costs for dredging. We have also other means like flushing, where there's a lot of also costs involved, like you cannot produce electricity, or you can have economics importance when it comes to ecological, like boundary conditions at fisheries. They want some payment if you flush. So we have to be very careful how to do this job. And we have, of course, a socioeconomics importance. So when it comes to sedimentation, we might have higher water levels, which increase the flood risk. So there's also a need to include other boundary conditions for this. And then we might have, like here is a little bit small, but you might have a sedimentation in a reservoir over 30 years or 40 years. And then you get a big flood, they open the gates, it's erosion here, and starting sedimentation again, and then you have a big erosion. Now, if you only do this unintended flushing, you might get sedimentation in the floodplains of meters, like we had it here in two floods in 2002 and in 2013. Each of them had about 4 to 5 million tons of remobilization, ending up in the floodplain. A lot of court cases came up, who is responsible for this. So then the hydropower company might be asked to pay for the damage. So even for them, also from this point of view, it's interesting improve the situation there. So coming to the example here, one example is then, of course, surplus of sediments. You see the reservoirs are filled up, like this one here in Spain. It's completely filled up, and you see the person here, and then the hydraulic engineering solution immediately was there to make it double the height. So you increase the height, and then the argumentation was you have even more space there because the valley goes larger the higher you go. So you can solve it for this, but this is not fully sustainable, we think, because then we have just the problem postponed to the future, and the structure is very costly, and the risk is high. If some damage goes to the dam, then all the sediments are immobilized at the same time. And we have all sorts of other processes, like here, colmation processes, which is for fish an issue when it comes to fish eggs, that they have no oxygen supply afterwards. And the opposite now is erosion downstream. Now you see some example here. If you have here a situation like in this picture here, in the right side, you may see it. There is gravel above here and fine material below here. Can you see my mouse? I'm not sure. Then you see a line from gravel to fine material.
Yes, we can see the mouse.
Thank you very much. So then this is a magic line. You know, this is just a schematic drawing. Now this means in many rivers you have gravel somewhere, or sand, or whatever it is, and you have finer material, in this case sand, also silt and clay below there. Now the issue is that this might be only a few meters, 10 meters, maybe even 20 meters, but you have a certain erosion rate, like you see it above here in centimeters per year. You see the Danube, the Salza, some Austrian rivers here, they get some erosion. Now this line is the zero line here, and you see how far they are away. This river, Salza, is close to zero, meaning close to this line, maybe half a meter left. Now, if you have for this river 7 centimeters per year erosion and half a meter left, you don't have to do research in order to calculate simply how many years you would have until you reach this line. And if you reach this line, you get a canyon type of erosion. I mean, this is the extreme case, just to show you it's not always like this, but it can be like this. And then, of course, the fish cannot spawn because they cannot jump on the dry gravel bar. For the next flood, you have here an issue, and so on, or you have a bridge somewhere that might collapse. So we don't want to get into this area. So this means we have to get the sediment somewhere downstream to avoid this riverbed breakthrough, as it is named. And if it is not like this, then you get also a lowering by 1-2 meters, and then the groundwater level goes down and all other risks are still existing. So you see this here, this was the magic line, you know, with zero gravel to fine material. Now we had here in 2001 half a meter left. They said we have 10 years time or whatever to react, but it wasn't done, the reaction, no measures were taken. And within a few hours, in 2002, you get 3 to 4 meters erosion into the fine material. So then it's quite difficult to do a nature-based solution, for example. And this is, of course, a George Arnold's slide here to show you again another example that you have the sedimentation of the reservoirs. And we know that this is an issue then, because especially with climate change, when you have here the hydrological variability, this means the variance between low water and high water levels. This is compared with the relative energy what you produce. So if this is 1, you produce the full amount of energy you can produce. If it goes down, then you can produce not 100% of what you designed your turbine for. So it goes down, all the line goes down. Now it is clear that with climate change now, we get a higher hydrological variability. We have dry years and then we have wet years, too much water, not enough water also from this side. So we have less than 1 here. But if we have climate change only, let's say, the minus, this line is quite high here still. So we are still close to 0.9 in this example here. But when you overlay this then with climate change and sedimentation, both effects, then of course this goes to this line. So you have only half of the relative energy available. So the issue what we are facing more and more these days is we have more variability on the one side, and a combination of climate change due to and causing, let's say, hydrological variability, and we have sedimentation additionally. So we jump down and more or less we fall down to this point. We have to avoid this because this is really a lot of economic losses. And if it's an irrigation reservoir at the same time, of course, a drinking water supply, it's even worse, like in African basins. If you scale this topic up to the global scale, then what you see here is constructed reservoirs since the beginning, a cumulative volume of all, including the Brazilian reservoirs with cubic kilometers of volume what we have until 2020 here. So quite accurate data, or recent data. So you end up with here the 7,000 cubic kilometers of storage. Now, if you look, so that's the construction. So it goes further up. But if you look into the net storage, what is really in the reservoir, you see these lines here, and they are stagnating, even going down. That means we lose, obviously, almost the same amount or even more volume by sedimentation on a global scale. Now we build new ones. So we build and build and build new ones, but we lose even more volume than we build. So I don't know how it is in Brazil. I would have to look into the Brazilian data more in detail, but it would be interesting to see, what is the conditions. But this is not sustainable, we think, because this costs a lot of money. And if we have not more available, what is the meaning of this? And it's even worse if you divide it then by the per capita. So you divide it by the people on this planet, and then you see this line here. So basically in 1970 or whatever it is here, we had the peak. So if you divide the volume per person, because of the sedimentation and because you get more people on this planet, we get less reservoir volume. Now, if we go for the existing volume, then we come back even to 1960 or something. So this is really a dramatic development, we think. So we get less volume, and if we calculate it per person on this planet, it gets even worse. So we have to do something here, but it's obvious to you that you are aware of this, but I wanted just to make the point at the beginning that this is something we have to look at. Now, what can you do now? What can you do now? It's not hopeless, I would say. So we have to start in different areas, and I don't go through all of this time-wise. There's a paper which I can even send you that tried to work out a methodology like the hydromorphological evaluation tool, where basically we follow the schema I showed you before, this river scaling concept, to start in the catchment, to go to the river network, to go to the reach and local scale where the reservoir is. So in essence, what we do is we look into a catchment with the GIS analysis, we put all the reservoirs in, and then we calculate or we estimate, depending on the data availability, how is then the sediment supply into the system. In the most primitive way, we give some numbers here. Is the connectivity given or not? If it is not given, it's the number 5 already, and we get here directly to the reach scale, because then we get not, we have a situation that is a very dramatic condition for the downstream area. Or we can look into the sediment transfer here. It can be a simple formulation or a complex one. You can use a numerical model, but basically we give here also numbers. So how much sediment is then transferred from the source to the reach scale. In the reach scale, we look into the reservoir then with monitoring and look into the bed development, into the artificiality and the conditions, what you have to find. So if we go by this, then at the end you get a good idea of what is the situation. Now you could put it like this as well. What you can do then for the basin scale, as a consequence now, we say we need a catchment-wide sediment management concept. So is now, I can send you this as well. There's a European, very new, only 1-2 weeks old, I think now, a guidance document from the European Commission on sediment management, and there's also a description what is the contents of a sediment management concept, what should be in. The idea is to look into the catchment and to really get into the negotiations, let's say, or the discussions between the different stakeholders. How do we manage the sediment in a better way? In this sectional scale, we have management measures in sections, and as you will see in a few minutes, sediment management at the hydropower plant itself. We have not to forget, it's not the topic of this talk, woody debris. So we get a lot of trees in there which block the outlet, for example, or which blocking screens. So we cannot forget the trees as well in this equation. On the local scale, of course, we can do also something. We can optimize the structure, bypass systems, as you will see. We can do something against erosion when it comes to free-flowing section. We can do something for the environment when it comes to spawning places. We need to do a model development, of course, and also we can reduce soil erosion. However, I have to say, and we have colleagues, of course, here with Tobias and so on, that we have here process research needed, of course, still in order to improve our equations, but I'm not talking about this today. We need also to improve the monitoring methods and the modeling and also the understanding of the processes in order to be able to improve our measures at the end of the day. So this is just schematic. Now going more concretely to issues. Now let's say this was a result of an Interreg project we finished 1.5 years ago from the Danube River, the Danube so-called Danube Sediment Project. If you can Google this or want to Google it, you find documents also there. And one document is this Danube Sediment Management Guidance. And in there, we had a schematic starting point to say we start here in the catchment with different measures and we go down, in this case, even to the sea, if the river is, let's say, looked at in the full sketch. So we have here land use, afforestation, we have improved sediment continuity. We have here the impoundment and the reservoir flushing, bypass turbidity currents with the free-flowing section with widenings, and we go to the dam, but you will see in a few minutes more details on this, on the weir height, especially on the width of the weir of the dam. The sediment turbine is one idea, large bottom outlets are also ideas, or to take the sediment out and to redump it on the downstream side. Sediment feeding is also one of the topics. So also here we look into the reservoir, but we don't start only here, we don't only end here. More systematically, what can we do now? So I want to focus on the right side here because this is for free-flowing sections, but this is something for the reservoirs and the impoundment. What can we do now? Of course, we all know we can have a change of the sediment regime. So we have 4 ways in this more schematic drawing. We have here the sediment regime. We have the routing of the sediment. We can increase the energy slope if we want to increase the transport capacity, or we can increase the bed shear stress as a part of this. And this is just a simple equation where you see then the comparison of the sheets parameter with the critical sheets parameter, and you all know this, I guess. And then what is meant here with the energy slope is here the S value. So if you increase the energy slope, of course, then the sheets parameter is increasing. Or if you look into that, in this case, the shear stress is the product of the hydraulic radius times then the slope. So we have then to look into also water depths as a synonym of the hydraulic radius for certain conditions. Anyway, what can we do here? We have here in the sediment regime to discuss, to control the sediment input. In this case, to maybe reduce it by land use change, by vegetation management. But we can have also relocation of sediments by mechanical excavation, hydraulic scouring, or whatever. Then on the other side, we have the routing here, and I will come back in a different slide on these measures to get the sediment through. Here, for example, the reduction of the weir height is one option, or to draw down the water surface when it comes to flushing. Or here, to increase the shear stress, we can increase the discharge when it comes to a bypass system, or we can optimize hydraulic structures like groins or guiding walls. So guiding walls and groins are ways to increase the shear stress. So however, there are different ways and different costs associated with this. And this is, of course, a detailed analysis that should be done in order to find out the best option or the best combination of measures you want to do. Now, in a way, you can put it like this as well. It's more or less a similar thing. We have the catchment-wide measures, the measures in the reservoir, and the measures at the dam. I want just to focus on some of them time-wise. like the bypassing, just to show you some drawing on this. Hydraulic dredging, turbidity control is one option. Sluicing seems to be a promising possibility, or venting of turbidity currents, and also pressure flushing of outlet structures could be one way to go. What does it mean now? Now, if we go here for sediment diversion tunnels, this is a very costly measure. And there are examples done, for example, in Japan and also in Switzerland, for example, where at the upstream and at the intake here into the reservoir, you might use a sediment diversion tunnel, which was built during the construction to simply guide the sediments around the reservoir and directly into the downstream area. So you can do it also in the middle. You need a guiding wall to transfer this sediment downstream. It's not so easy. It's costly, this example, and one has to look into the abrasion of the concrete because it's very steep, might have very high flow velocities in there, and you might have coarse some material to put downstream. But there are quite good successes in Japan, for example, to regain eroded coastlines to get back the sedimentation in the low area. Or you could work with turbidity currents like here, where the idea is that you have suspended sediment-laden water or even small-scale bailout, but more for finer materials. And then you simply open the bottom outlet and let the reservoir as it is. The reservoir height is not, the water level is not lowered. The thing is that if here the input water is cooler than the water temperature in the reservoir, you get a so-called plunging point, and this density current, it dives down to the bottom of the reservoir and is transported at the bed of the reservoir to the dam here, and you have here the bottom outlet, and so the sediment is guided through the reservoir and goes to the downstream area. And this is what we can help with different means in order to get it done. It's not always working because when you have here some perturbation, then you have to support then the turbidity current to be formed, or it can be even destroyed on the other side when you get a lot of turbulence. So it's not working everywhere, but it's one possibility to go for. To give you the example which I started with, the first slide here, this reservoir Sölk, then what you can do else also is to have a let's say two-chamber reservoir. In the upper part, you have a reservoir where the coarser material is deposited. Now, either you have a sediment bypass or you would have to dredge and to redump it downstream if possible. But the good thing is that the coarse material does not enter then the main reservoir. It's a pre-sedimentation area, and there's a ramp differentiating the pre-sedimentation area from the reservoir itself. In the reservoir, you for sure get the fine sediments, as you see here with deposition of the material and then the trees and so on around it. Now it becomes an optimization problem. This is just for this reservoir and an analysis done. Now what you see in this here, in this diagram, is sedimentation on the x-axis. It starts from 0, no sediments are in the reservoir. It ends up with a completely filled reservoir. And you want to look into flushing in this example, so you want to draw down and to flush the sediment out. Of course, if you have no sediments, you don't have to flush basically. But if you wait too long, the reservoir is filled and you cannot flush anymore because the bottom outlet is completely blocked. Now we have here some measurement points, and our assumption is, and the model results show a little bit, that we have somewhere an optimized sedimentation. Why optimized? Because we use here the flushing efficiency. The flushing efficiency is quite simple. You compare the volume of water and the sediment concentration that comes into the reservoir with the volume of water and the concentration that goes out of it. And basically it means that you want to get as much sediment out of the reservoir with as little water as you can use. So with a small amount of water, you get much sediment out. Of course, this has ecological implications because the concentration is then very high. But we think there must be somewhere an optimum where you have the highest efficiency for flushing. This is a technical issue. If you do it too often, it's too expensive, doesn't make sense. If you don't flush at all, you get a technical limitation. You can't flush anymore. But now we have an ecological boundary condition, as you may all know, what we call here the stress index. And this is related to fish mortality. How many fish are dying? If you have 100 here, 100 fish out of 100 is dying. So all fish are dead at the end of your flushing. Here, no fish is dying. And this is a line here, the stress index, the blue line, which is calculated with this formula, simple also. You just multiply the concentration with the time, a logarithm in there, and then you see here this distribution. And then you can select yourself. If I flush in a very high concentration, I can do it only for a short period of time in order to stay in a certain limit with the stress index, or I have a smaller concentration in milligrams per liter and a longer time I can have for the flushing. So we have not, if we go for this optimized thing, we have also to look into this then, what does it mean for the fish and the environment? And we have a third one, which here in the most simplest way, of course, we have the economics calculation. So if you flush for 4 days, in this example, you lose about 5 million kilowatt hours and you lose about 120,000 euros already with this flushing. So from the economics point of view, you want to be very short. But if you are short in flushing, you might have high concentrations and you might have here an issue. So all I want to say here is at least we have 3 optimization functions, or let's say points or parameters we have to look into it, if it is flushing in this case. So like the efficiency, the stress index for the environment, and the economics calculation of the losses you get. But the hope is then, if you do this, you would want to get to this kind of optimized situation. This is not flushing anymore maybe, but another like density current, because then you wouldn't have to flush. You would not even get the sedimentation anymore. You would let the sediment go through. That would be the best case. And then if you do it too often, you lose money. If you do it not enough time, frequency, then you get an issue and you can't flush anymore. So we can, for each reservoir, define basically a line like this and identify what is the best way for my reservoir here to get forward. Now, to help you a little bit, we did a World Bank project together with Pravin Kaki. We had also, I think, a seminar in Brasilia together. Some of you might have been there. And we developed, in the meanwhile, the project finishes now, is finished already this year. We have products which you can download soon in a few weeks, hopefully, which is this one here, ResConDo, which is not a numerical model, but it's a kind of a way to estimate, and in a very simple way, in a way to get the first idea if I do sluicing, tracking, hydrosuction, dredging, flushing, what is the cost with it and how is the efficiency? That's one way to go into this. This should be downloadable soon from the World Bank, and I'm sure that Nikos and a colleague from me here who did the programming can support you if you want to do it. It's a very fast method to get a first idea which measure would work, and it should be published in a few weeks actually. A second tool is the Reset. It's an Excel toolkit. It's also very simple, I think. There you can really use it in order to get like this one here, simple calculations where you can get sediment rating curves. So you can rating curve adjustments if you put in your data. It supports you with the simple estimations of the trap efficiency or parameters we use there. And of course, we can also go to modelings of the soil erosion, but soil erosion is, I think, another domain, another topic. So some toolkits of this project might be available soon. If you want to look more detailed, let's say these are more qualitative, not qualitative, but they are more non-numerical too much. They are calculating things, but not a simulation model. Now, of course, if you want to go more in detail, we can do, of course, or you can do a sediment transport study on the catchment, like this was an example, also in the World Bank project in Bleninger 4 Reservoir in the Philippines. So we went there, did some field work together with the colleagues at the University of the Philippines was involved. Unfortunately, Corona came then, and there was not too much time to really get so much forward as we wanted. And then you can do a numerical study, like you see here, the water depth simulation with a 3D model in this case. And then at the end, we built also a scale model in order to see concrete measures, how they would work. So this means the outcome was here a certain, let's say, flushing channel, which reduced the sedimentation. This you can see here, this is this flushing channel. So you would have to dredge this. And then when you really operate it in a wise way, then you can reduce the sedimentation significantly. You don't have to dredge everywhere. You have just to open, or let's say to keep this channel open. But this is not a general thing. We have to really look into each reservoir in a way, what is the best option. Now, what options do we have now here at the reservoir in a smaller scale? On the one side, we have, of course, here different measures at different scales, so catchment, ridge scale, local scale. And we have then differentiated it here in the reservoirs and the dams here. So for today, it's more or less this part we look at. And then we have the free-flowing sections on the other side. We don't look into the measures here. So it's a list of almost 50 measures. And also, if you want to look at it in detail, there's a report in the Danube Sediment project, which is called Sediment Manual for Stakeholders. So these measures you find there, and you can read the description of the measures there in a general way as well. Now, not to take too much time now, I don't go into the sediment management measures in the catchment. There are different ways to look into this. And of course, here also the agriculture has to be taken into account, which means then to reduce the surface, for example, runoff by infiltration or retention, to change the land use, they have not bare soil anymore, and so on and so forth. And then, of course, we have here the measures in the reservoir. I want just to focus here. And here's something written. You will see in a minute in some sketches. So I don't go through them in this slide, but this is a way to have a kind of a, I would say it's a menu. Like if you go eating, you can see what is offered. And then, of course, it's up to you as an expert to see which combination of measures is working. It's not one takes it all. So we have to go into them and to analyze them with tools like Rescon and others to find out. So we have measures at the reservoir in the impoundment, and we have measures differentiated at the dam. At the dam, we have here different measures. You can see, but I will go into them a little bit more. Now, this is maybe small if you have a small screen, but you can, as I said, download it, or I can send you the link, or I can send you, if you want that, even the document as a PDF. You can have it if this is the better way for you to get the information. So all of this can be read there. But what do we have here? For example, here, minimize the width of the impoundment or the reservoir. So we have to look into the reservoir in a way, because we think nowadays that, of course, when it comes to runoff schemes in this case, that we have to have a certain transport capacity when we have a flood and when we want to open the gates here, so that the sediments can be put forward outside downstream, in this case of the reservoir of the impoundment. If it is very wide, then we get extensive river sedimentation of material, and this is then a planning issue. Unfortunately, in our conditions in Austria, we have many reservoirs where sediment was not a part of the planning process. It has to be an integral part of the planning process, because then you can much more, let's say, get a better output. So the reservoir configuration is very important. Having a narrow reservoir when it comes to runoff schemes, of course, in a reservoir in the alpine environment, it might be different because you need the volume. But here, just the water flow is important, not the volume. So what water flows in goes out. In this sense, we can be small and we can reduce the sedimentation by increasing the transport capacity. Or another issue, like this is for reservoirs, like here's the reservoir. You want to bypass with a tunnel to the downstream part, and we want to avoid the sedimentation here. As I said, time-wise, I don't go into details, but you can read here also ideas what the effects of the measures are, what is the scale of the measure, what do we have to assess and to monitor, what are the risks with the measure. And this is not a planning for a concrete measure. It's more or less the way to describe what the ideas you can get out of this, what could be done there. Or another one is to optimize the flushing and sluicing strategies for dams in series. If you have runoff schemes in a series, of course, there is then a certain coordination needed for the water level drawdown with an adequate timing between the two hydropower plants. So you need to know the flow time, but also then you need to know the transport time for the sediments. So you wouldn't want to erode some material in one reservoir and then you get deposition in the next one. Rather than that, you want to get the sediments through, which is not possible for a very coarse material maybe, but for fine material it should be possible. Or you could, of course, go for dredging and reinsertion. There are even SETCON and other tools. You dredge here in the upstream part, you have a pump, and of course you have here a pipe going downstream, and so you transfer artificially the sediments from the upstream side to the downstream side. And there's even a robot that nowadays discussed that can go like a mower for the lawn, for the grass, goes along the bed of the river, of the reservoir, and all the time takes the sediment out and transfers it downstream. Of course, this is costly and there's energy needed and so on. So maybe it's of course an option, but if possible, we would want to avoid it, but sometimes it's necessary. Now for the dam, now we go from the reservoir to the dam, so to the local scale. Some examples here. So what we think is an era, looking at the pictures here. You have a runoff scheme. It's a small hydropower plant here, not too small, but a smaller. Normally, we would have this configuration. We would have the powerhouse somewhere. Sometimes at the dam, we would even have sluices for the ships. Or we have here the weir fields, which we have here on one side. So automatically, if you add all that up, you get to an increase of the width here. In an ideal condition, you want to have not a too much change of the width. And you can do it if you put the turbines outside. Maybe you have here different configuration in general, or you put even the powerhouse outside of the river here. So that the width, anyway, the transport capacity, this is a big topic. In almost all hydropower plants, this is much larger than the river width. And when it is larger, and we did some scale models, I could send you also a paper if you're interested on this. The width, of course, determines the sedimentation, and so we want to have also not this big increase here. This is a planning point. The second planning point at the dam is the weir height, the fixed weir sill height. So the concrete, more or less, you see, this has a very high concrete here, and the movable gates are there, and here the concrete is lower, and the movable gates are larger. Of course, it's quite obvious. If I have this condition, I open the gates, the slope that develops again is much higher than here. So in this case, unfortunately, many power plants were built in this way because maybe the movable gates were too expensive, but then the slope doesn't support your flushing, for example. So you don't get rid of the sediment because this is a fixed point here and the slope is not large enough. So we are advocating these days to rethink in planning to get as low as possible with this concrete part. If, of course, you have to think of the sedimentation of some other topics, but in many ways this is possible and described here. So minimize the width increase and minimize the height increase in terms of the concrete what you have there. Even at the runoff schemes, you can go for bypass systems. Like here is a tube, a pipe you can put into here. In that sense that here is the powerhouse and here's the head race. You have a so-called vortex tubes with a spiral flow there. So the sediments that go towards the powerhouse, and it's also fine material, you know, it's diverted back to the river. So we can have this kind of pipe to go back to the river. All that is also in text described in this document. Yeah, I think for the Bleninger, I already mentioned this, that there was there's also physical models possible, obviously, which in some cases would support before you implement it and it wouldn't work, you should maybe go to a scale model as well to test it. And then if you do this, of course, you can see the difference here from the reservoir silted versus the dredged or free of sediment situation for the efficiency of sluicing and flushing. In this case, it's a combination of sluicing and flushing. The focus is on sluicing. Now, what is this difference between sluicing and flushing? Sluicing just means that we can open the bottom outlet without lowering the water level. and the sedimentation would not be taking place because the sediment goes through and the flushing efficiency is high. Or another last example before I finish is another reservoir, just to show you here. And this is one idea. This is very wide here. This is more for coarse material even. You want to get the coarse material through the reservoir. You never get it through, despite you would have some guiding wall here. It's dividing the reservoir. And then you have some success of concerning a comparison of the sedimentation over time. And what you have here is, let's say, for this the orange line here, you see no sedimentation over time. This is this canal, more or less, a channel in the reservoir. There's no sedimentation here. Of course, you get sedimentation there, but for the coarse material, you get the sediments through with such a configuration. This is just a picture where it is. You see the guiding wall here. If you look into the animation, you can see that the shear stress here in newtons per square meters are building up, and we have high shear stresses here, so the coarse material can go through. Of course, we have here lower shear stresses, so we might have fine sedimentation here of fine material sedimentation. But if you would want to get the bed load through, as you saw here, then you would need this higher transport capacity in order to get the sediment through. Yeah, that's not important, I think, to go through, because it's just more or less a similar situation, but just comparing with the guiding wall and without the guiding wall, and you see yourself the difference. If you have not the guiding wall, you have a breakdown with only 0.6 or 1 newtons per square meter shear stress, and so all the coarse material is also sedimenting here, and you would not want this. But of course, this is just one example, one way to get the coarse material through if you want to get it through. This is again then another kind of artificial, let's say, concentration. You see the high concentration that it develops also in here in the transport canal for the suspended sediments. So also the sediments go through here. Now, to finish off my talk, not to be too long, what I tried to discuss with you is here that we have this increasing gap between the surplus and deficit of sediments. So the sediment balance is not existing, but we need it for climate change, land use change topics, and to keep the sediment, the reservoir volumes. Now, in the global sediment management study with the World Bank, there's a provision of case studies and tools and policy guidelines, etc. I can provide you with this information, but also from the Danube Sediment Project, there are documents which I can easily send to you, and if you want to look at that. On the other side, we need a process understanding, so we need to look into the scales. Again, to come back to the beginning, and not start only at the dredging, but you should consider the larger picture in a way, if it is even qualitatively, but not only to look into the reservoir. So the scales are very important. And then we need sediment management measures that are sustainable, and they lead to a sustainable reservoir management. And that can be quite many different measures we can select, and you would have as an expert to select what you would want to go. At the end, of course, we have still some research demand that is necessary for the processes. Of course, we see that even to calculate initiation of motion with a Shields diagram is not fully the truth. Also, the formulas we use, they might be very old. So we need to go to large-scale physical model studies. If you would come to Austria, I would be happy to show you. We just built a new lab here with a discharge of 10 cubic meters per second in the scale model, just diverting the Danube water with a natural waterfall for 3 meters. So we can. The idea is to get a one-to-one scale sediment models without having to scale down the particles, because this gives some, for example, with cohesion, some other processes they are disturbing. And of course, field monitoring. I know that Anna and Brazil has a long tradition in all this research and also in the monitoring. And I think they are very exciting, and I didn't talk about this today. Field monitoring tools and methods, but also numerical modeling is quite developing, I would say. The only thing is with the numerical modeling that they can only be so good as the data you put into the model, and especially the mathematical descriptions, the formulas you use. If the formulas don't fit, then of course the numerical model doesn't give you a quite good answer. So this would be also an outlook in the sense that we have to do more in this. And this is more or less my talk. Thank you very much for your attention. And of course, I'm available for questions.
Thank you very much, Professor Habersack, for your excellent presentation. We get some questions here. And the first one was from Diogo Barque. He congratulates you also to the excellent presentation. And his question is, sediment reservoir management includes monitoring, which may not be easy in some cases. But how to evaluate the possible downstream impacts as a way to best decide management operation, mainly in constructed reservoirs?
That's a very, very important point. And in principle, what we have to see is we have to differentiate the coarse material from the fine material. When it comes to the fine material, let's say smaller than 1 millimeter size, suspended sediments mainly, then of course we have to look into different processes. One is to look into the concentration. Like in our country, people say that if you increase the concentration more than 1 gram per liter, then they would ask you to stop the flushing if it is flushing. So what you have to do is to monitor the sediment concentration downstream with a turbidity sensor, with real probes, whatever you have, with an ADCP additionally. So then, of course, but it's not the truth only because some fish can sustain higher concentrations, but it's also the timing. So we are right now do some research project in order to show that it's not always this 1 gram, it can be much higher, but if it is only short, and I told you this stress index, so the concentration, the time we have to observe, but also if possible, the distribution of the sediment cloud, because fish might find in the cross section some area where there's lower concentration. It's not, the concentration we measure at the riverbank is not continuously over the whole cross section. We all know this, so we need to know a little bit more about the distribution of the sediment. For this, we can use an horizontal ADCPs, for example, or we have a bridge. We take different samples. That's for this. For the coarse material larger than 1 millimeter, of course, there are long-term effects like the bed level changes. So it's quite clear we have to measure the cross sections downstream and to see what is the change there. But we should also take from time to time grain size distributions, because then we see, is the erosion leading to a coarsening of the riverbed? Does it get finer? So the grain size is another parameter there. Additionally, also the morphology and so on. That's more or less from this side. I could talk too long about this, but I guess this is some parameters we could have, and of course, also the environmental parameters.
Great, thank you. Another question was from Rafael Brandão. In your opinion, what is the most effective measure to control sedimentation of reservoirs located in urban areas?
In my point of view, is the most important thing are 2 points. We have to design the dam with enough large, let's say, bottom outlets. We have to have, or weirs, movable weirs, or gates. So we have to, and as I said before, we have to lower the concrete. So in the best case, you would open the complete cross section during a flood, and then, or if it's not possible, having let's say having then bottom outlets if this is a higher dam, and so the width should be small at dam side, and the slope should be large, so the concrete should be lower, and of course that means also in terms of the timing. So you need a weir order, or how you call it, during a flood you have certain needs legally binding how the hydropower company moves the gates. If they move it too fast, they get a surge effect. But for the sediments, there's an optimized way. Actually, we want to maximize the energy slope. So in this sense, you would have to calculate in which speed you open the gate. So make it small, make it low the concrete, optimize the motion or the management of the gates. And try also the reservoir not to build in the track type form, but make it slim. But of course, if you have a reservoir where the volume is important, we have to differentiate the runoff schemes from the reservoirs we all know. And for reservoirs, it's a little bit more tricky, but then you have also to do some, let's say, calculation beforehand. If you have some structures in the reservoir, if you lower the water level, you get an increase of the shear stress, maybe groins or other structures. If you have the chance to get a colder water into the reservoir, maybe the option of not flushing, sluicing, but also the turbidity currents could be good. No general answer possible, sorry, but
Thanks, Daniel. And Pedro Cunha is also congratulating the presentation, and his question is, I would like your opinion about the techniques and methodologies which are more appropriate for Brazilian reservoirs. Especially, what is your opinion about to define a limited increase of 5% deposition for specific reservoir sections before doing management or something like that?
Yeah, I think it would be good in a way, if possible, to start with the basin. I wouldn't say analysis, but there's a basin understanding, basin-wide understanding. So the basin, where's the sediment coming from? If you want to really start with this, because it might be that you design some measures at the same time you get deforestation in some area. We all know this intensification of agriculture. I think also in Brazil, but in many countries. So you might get more sediments in at the end for fine material. So we have to see what type of catchment is this. Is there a risk to get more agriculture with more soil erosion? Then your design of the reservoir from the beginning should reflect this. It's just one point. The second one is it a chain of reservoirs? So you are in the middle somewhere. Are you at the upper part or are you in lower part? And what is this situation? Because if you have a chain of reservoirs and you are in the middle, your options are less, of course, than if you are in the higher one. But if you are in the higher one, in the upper one, then you have a great responsibility because whatever you do, you give it to the next one. So and if you are an isolated reservoir, only you are there, then you have more options. That's maybe a better condition then. And then you can say, I want to design my reservoir that I have a model done or whatever. In order to say I want to have 5% sedimentation, how can I design it in a way that I do a more frequent flushing, for example, every year, or 0.7 times HQ1. The tendency nowadays is to have a more frequent operation. Of course, you lose some water, and that's depending where you are in Brazil, I guess, as well. Because if you lose the water, it might be an issue if it comes a drought afterwards. But in a way to get a more frequent management done, that doesn't mean at the end that you lose more water because you have on the other side kept more volume of the reservoir. So it's a question of the width again, of the slope again, but also the structures in the reservoir, the dam, of course, and what you can allow, because if you have downstream, because of your configuration, for example, either another reservoir or you are close to the sea, whatever, it would be different compared to a far upstream reservoir. Also in environmental conditions. So you need to know which fish you have, how much sediment do the fish withstand. It's also not a simple answer, I guess, but I think there are many options these days. And also you have excellent researchers as well, and so that there is a possibility to really look into that. But don't start again at the reservoir. Yeah.
Thank you. Actually, Pedro Cunha was adding a comment that he's from the National Water and Sanitation Agency. So they thought about that 5% deposition increase being an alert for asking for new measures or additional bathymetrical surveys. So it was in that sense.
In that sense. Yeah, I think that is an alert that is really true, but I would say even independently of the 5%, a regular monitoring is really needed. Without data, you can't really do anything. So if you can manage to get every X years, let's say, depending on the sedimentation rate and morphology of the reservoir, but maybe even grain sizes additionally, then it's good. And that's very important.
Thanks. And this brings me to my question, actually. It's about how you measure reservoir sedimentation. So we did quite some studies here at one specific reservoir using bathymetrical surveys, but also using sub-bottom profilers. And this provided us actually volumes, but not mass. So, and we recognize that the reservoir bed is it's like a pudding, so it's very fluidized beds. So the volume does not necessarily inform about mass. Then we used sediment traps. They actually provide sedimentation rates, but only for short periods. And then we also used sediment cores, but taking the cores out, they're disturbed. They provide mass and volume, but they're only point measurements. So it's very difficult to get, and comparing those and actually comparing those to the catchment input, we got very different numbers on sediment mass and volume. So what is your experience on that? Which methodology you would recommend?
Yeah, it's also, I think it's not one methodology, it's a combination, as you also say, it's a combination. Actually, what we use here is multi-beam eco sounding to get, of course, it's really a 3D model at the end you get. So sometimes we have 50-meter distance cross sections with single beam, but so eco sounding, but I think that the future is more the multi-beam, so we get really a 3D model. This is quite accurate, this one way. So we need somehow the surface of the sediments. And then we found out, as you say, where is the surface of the sediment? Even the eco sounder has some uncertainty. So we now test a new methodology to give you, it's not published in our case, which is then, let's say, seismic profiling, it's named seismic profiling. So you have a special instrument which is able to penetrate into kind of a radar signal in a way. It goes penetrates into the sediments, and when the density is changing, you get kind of a different structure or even a line at the end. So you can differentiate the fine material, that's our hope, from the coarse material. And it's, as you say, it's still under investigation, but we saw up to now that could be quite promising. So you have to calibrate it. In a way, you go there, you take volumetric core samples. So we take core samples additionally. And that's another thing. We take core samples and do some sort of analysis in the sense that what is the specific density, for example, and what is the also we even use it for kind of a scale model to get the shear stress needed for the erosion, because we know that cohesion is there. So we look into cohesion, and then it makes a difference if you have clay, as you always know. So again, I think there's some examples what I would say, but you need to combine these things, and everything starts, I guess, with the volume, with the bathymetry plus could be seismic profiling as one idea. If you have a paper, I can send it to you, but it's not written yet.
Thank you very much for that. And another question of mine is actually related to the differences in tropical reservoirs and temperate climate reservoirs. So what we observed is that actually in tropical regions, we had quite some sedimentation due to algae growth or other processes, so internal processes, not coming from the catchment. And another process, what we observed, was bank erosion. So just the winds blowing and then bank erosion, reducing increasing sedimentation. But we weren't able, or I haven't seen any study quantifying that. So do you know about reservoirs where sedimentation is dominated by those internal processes instead of the inflows? And is that something we should look in more detail, especially here in those tropical regions with high internal production, or is that something which is not that significant?
No, I think it is a big topic. We don't have the tropical rivers here, but we have one lake. We have one lake that is on the eastern side, Neusiedlersee, and this lake is a shallow lake with high water temperatures. And there we observe what you just say, that especially when there's a dry period and then the water level is lower, or the usage of water is much higher, then we get these decomposition processes there, and the algae blooms and all the organic material, and even then changes of the chemical composition, and then you get sedimentation of this material. And also even in the river had recently these kind of biofilm, excessive biofilm structures. I agree with you. We have generally to look into this, because the biofilm itself then hinders the capacity for flushing, because the shear stress, the critical shear stress, if you compare no biofilm with biofilm, it might be 3 times higher. So you would need 20 newtons per square meter, suddenly you lose 60 or 100 you would need. So the biofilm, quite a complex structure, as we all know, with bacteria combination with other structures that get there as one indicator. It's not what you said only. You said about more processes, but definitely I agree. It is a factor.
Thank you. That's very interesting. I haven't thought about the biofilm and shear stress effects on that. Very nice for that. I think we can go to the last question. Is again from Pedro Cunha, which is a more general question, asking, in the project like Danube River, do you think it is applicable for the Brazilian situation, like the Pantanal region or the Paraguay Basin?
To my point of view, it is, you cannot do one-to-one the same, I guess, but the idea could be the same. The idea would be, because I know that there's a lot of data by ANA and available. So in a way, what you would start with is to try to build up a sediment budget in a way. And even if it's not perfect, it can never be perfect, but you would want to start with a sediment budget, and then you would want to start with a change of the riverbed or the reservoir, the bathymetry, and then you start combining the sediment budget and comparing the sediment budget with the changes of the morphology in a way, and so on. So at the end of the day, you might, of course, be able in the Pantanal or in other areas to really get kind of a compartment of dominating processes, I would say. You might have areas with this, of course, sedimentation, erosion, but how much sedimentation, how much erosion? And at the end, if I would be optimistic in a way, knowing that you have many data already. But even if not, you would have to measure some of the data additionally. But to get a first idea, and even if it's crude, even if it's not very accurate, but it's better than what is in many rivers, also in Europe, available. Because if you don't have any of this analysis done, basin-wide, and also including the reservoirs, then it's very difficult to do a management, because what is then the target and what is then the success evaluation, what is the reference you look at. So definitely, I think it's completely different processes maybe, or whatever, the conditions are different, I guess, but the approach and let's say the parameters or the methods can be comparable. And I think that not one-to-one, one cannot take it, but I guess that it's possible to get in this direction with different, of course, specific topics and specific methods and so on. But the basics, look into segments, that's for sure possible, to my point of view.
Great. Thank you very much for your inspiring replies and your talk. So we really appreciate that. Before closing this session, I'd like to announce that we have a virtual cafe actually starting right after that session for the audience to have a chat, to interact. It's possible, so everybody is invited to join the virtual cafe. Just go into the event platform and link in. And I'd also like to announce the talk, the roundtable actually at 3 o'clock, which is chaired by Pedro Cunha, about sediment management in reservoirs, gestão de sedimentos em reservatórios. So with that, I really thank again, Professor Habersack, for your talk and for your replies. Another applause for you. And thanks to the audience for the questions. in my
Thank you very
first
much. I
session.
hope to see you again once physically.
Yeah, would be great. Would be great. Looking forward
Have a
to
nice
that.
day. All the best. Thanks for the invitation. Bye bye.
Thanks, you too. Bye bye.